All right, let's get right into it. We're talking Postgres, we're talking Pinecone, and we're talking about a vector stack that's potentially 96 times cheaper. For a long time, if you wanted to build a serious AI application, you knew one thing for sure, you were going to have a massive bill for vector search. But what if that's not the case anymore? Today, we're going to break down how a pretty amazing open source approach right inside Postgres is completely shaking up the game.
So let me just ask you this straight up, because it's a question I think every developer, every founder, every CTO has been wrestling with. As you scale up and your embeddings go from millions to billions, is your vector database just setting fire to your budget? It's a huge pain point, and frankly, it's not sustainable.
So how did we even get here? Well, the problem is that for the longest time, high-speed vector search meant one thing. You had to use expensive in-memory architectures. The basic deal was, if you want that real-time, snappy performance, you've got to load your entire index into very, very pricey DRAM.
Now, this slide really paints the picture. We're looking at the total cost of ownership for 100 million vectors. And yeah, at first glance, a managed service like Pinecone at 120 grand a year looks pretty good, right? Especially with that tempting $0 for operational overhead. But here's the catch. That cost is directly tied to their expensive in-memory infrastructure. You're not just buying a service, you're paying a massive premium for them to manage all that RAM for you.
And this quote just hits the nail on the head. With large language models causing this absolute explosion of vector data, the whole all-in-memory model is starting to look, well, a little crazy. We're talking about petabyte scale growth. Can we really afford to keep all of that data in the most expensive storage available? The industry is starting to scream, probably not.
And that, my friends, brings us to the breakthrough, the big idea. What if we could shift the bulk of that vector index from that super expensive RAM to much, much more cost-effective solid-state drives? You know, SSDs. This isn't just a small adjustment. It's a complete change in how we think about the problem.
And this right here, this is the whole economic argument in one simple image. The cost per gigabyte for RAM versus a speedy NVMe SSD, it's not even a contest. We're talking orders of magnitude cheaper. So the billion-dollar question becomes, if you can get great performance from SSDs, why would you use anything else? The potential savings are just astronomical.
Well, the answer is a resounding yes, you can. And the magic behind it is called DiskANN. This is a brilliant hybrid vector search algorithm that came out of Microsoft, and its genius is really in its balance. It doesn't just dumbly throw everything onto the disk. Instead, it intelligently figures out which tiny parts of the index are absolutely critical for speed, keeps those in memory, and offloads the vast majority of the data right onto the SSD.
Okay, so how in the world does DiskANN pull this off? How can it possibly search so efficiently on what's supposed to be slower storage? Well, the secret weapon is an algorithm with a pretty cool name, Vamana. Let's peel back the curtain a little bit and see how this thing actually works.
You know, the best way I've heard it described is that a Vamana graph is like a smart social network for your data. Seriously, think of each vector as a person in this network. It's not connected to everyone, that would be chaos. It's only connected to a handful of its closest neighbors, its most relevant friends. This structure creates a kind of super efficient map for navigating your data.
Now, to search this network, you use what's called a greedy approach. It's simple, really. You jump into the network at a designated starting point. Then, you look at all of that point's direct friends and figure out which one is closest to what you're looking for. Then, you hop to that friend. And you just repeat that process. Hop, check the neighbors, hop to the closest one, getting closer and closer with each step until there's nowhere closer to go. This is so important for SSDs because it means you're not doing a bunch of slow, random disk reads. You're following a smart, predictable path through the data. But wait, there's one more piece to this puzzle. It's called product quantization, or PQ for short. See, even with the main index on disk, you still have to load little bits of it into memory to compare them. PQ is this incredible compression technique that basically shrinks those huge vectors down into a tiny memory footprint. And the craziest part? It does it with almost no loss in search accuracy. It's like magic.
And the benefits are just massive. With product quantization, you shrink your index size like crazy. That means you can fit way more of your data into the RAM you do have, which means fewer slow trips to the disk. Plus, since the vectors are smaller, they're faster to compare. So when you put it all together, the Vamana graph on SSD plus PQ's compression, you get this unbelievable efficiency gain. And that's where that headline number comes from. Benchmarks are showing up to a 96x lower memory footprint.
Okay, so this technology is powerful, it's cost-effective, it sounds amazing. But where can you actually get your hands on it? Well, this is where it gets really interesting.
This brings us to the main event, the showdown. It turns out this game-changing tech is available right now inside one of the most popular, most trusted databases on the planet.
And here is the big reveal. The challenger is Postgres, supercharged with an open-source extension called pgDiskANN. That's right. The same DiskANN algorithm from Microsoft has been packaged up and integrated directly into Postgres. You get all the power of SSD-based vector search inside the database that you probably already know, and maybe even love. And the performance numbers? Well, they're kinda nuts. According to the benchmarks from the team that built this, Postgres with DiskANN gets 28 times lower latency at the 95th percentile and 16 times higher query throughput compared to Pinecone's own storage-optimized index. Let me translate that. It's way faster for your users, and it can handle way more of them at the same time.
So you combine that incredible performance with the massive cost savings of just using SSDs instead of RAM, and the economic impact is just staggering. The same benchmark is claiming a 75% cost reduction when you self-host this Postgres stack compared to using Pinecone. For any company, that is an absolute game changer for the bottom line. Okay, so what does this all mean for you, for developers building these systems? Well, it means we have a whole new architectural pattern available to us. It's time for a new vector playbook.
This new playbook is all about an idea called tiered storage. It's actually really simple and intuitive. Not all your data is equally important at any given moment. So, your hot data, the stuff that's accessed all the time, can live in a traditional super-fast in-memory index like HNSW. But the vast majority of your data, the cold stuff, can live on that much cheaper SSD tier, indexed with DiskANN.
And the most amazing part of all of this? You can do the whole thing, the whole shebang, inside a single Postgres database. You just figure out your data patterns, you create a standard HNSW index for the hot data, you create a DiskANN index for the cold data, and you manage it all in one familiar place. You literally get the best of both worlds. Insane speed where you need it, and massive, affordable scale for everything else. So I'll just leave you with this one last question to chew on. As our vector datasets continue to just explode in size, thanks to these ever more powerful AI models, is the old way, the all-in-memory way, basically a dead end? Because with technologies like DiskANN proving you can have incredible performance and scale at a tiny fraction of the cost, it really starts to feel like the future of search is planted firmly on disk.